My name is Anish.
My name is Yuval.
And I'm Frederick.
Hi, buddy.
So our project is the synthesis and comparison of the microplastic degradation efficiencies of magnetically removable photocatalytic microsumers. So just for some background on microplastics themselves, they're defined as fragments of plastics less than 5 milliliters in length. They currently comprise 11% of total ocean plastic pollution at 1.3 million metric tons in 2021. They are a threat to marine and human life alike through infiltrating our drinking water and eventually our food webs, leading to a larger impact of environmental destruction.
What we are using in our project is oxidative remediation methods instead of current membrane-based filters, which, for example, larger particles aggregate through, on top of the pores, blocking entry of smaller particles and larger particles. And that's not efficient. And also, smaller particles are easily able to go through the pores, which means that microplastics are not filtered correctly.
So now for what a microsumer actually is. Essentially, they are small pieces of metal that are light harvesting, and they are made up of two components. The first component is a photocatalytic metal. One way you can think about this, it's kind of like a solar panel. It takes in light energy and it converts it into chemical energy that can be used to do other things. In our situation here, it is just moving forward in a fluid environment. Then we also have a magnetic coating, which will be achieved through magnetite in our case. So the purpose of that is that if we just hover a magnet over our microsumers, they will be able to remove themselves from water. They are also self-propelled through utilizing the low band gap properties of photocatalytic metals and the H2O2 fuel that will be surrounding these microsumers in the chemical reaction that is ensued. Anish will be explaining that on a later slide. But these microsumers have been previously used primarily in the biomedical field, where they have been pioneered to transfer microscopic cargo and drugs across the fluidic environments of the human body. And now we're trying to use that technology in the application of microplastics. So now we'll use microsumer technology to collect small fragments of plastics in water environments.
Now let's talk about the science behind microsumers and how exactly they degrade microplastics. So here we have a simple diagram. We have a semiconducting material, and examples in previous studies include bismuth oxide iodate and titanium oxide. And here we have a magnetite nanoparticle. The magnetite nanoparticle allows the microsumer to be controlled by a magnet, so you can easily remove them from a solution of microplastics. And this semiconductor has valence electrons on the outside on its valence band. And this whole thing is in an H2O2 solution, which is going to be our fuel. Now, when light is radiated on the semiconductor, what happens is some of the electrons with the new energy that's being added get excited to a state that's known as the conduction band. And this difference of electronegativity between the valence band and the conduction band is known as a band gap. Now, naturally, we would want materials with a low band gap, so it requires less energy for electrophoresis, which is the process by which the microsumer moves through the solution. Next, what happens is the H2O2, some of it will reach these electrons that are excited to the conduction band, and it'll create H plus ions, O2, and also free electrons, but it'll fill in these positive gaps, also known as holes, on the valence band. Similarly, we have another reaction where these same ions and electrons will react with H2O2 to form water, and therefore remove electrons from the outside conduction band. So now, this O2 gas that we've created creates bubbles, and bubbles, like propulsion, causes the semiconductor to move through the solution. And eventually, it will reach plastics along the way, and it'll basically adsorb through van der Waals forces to these plastics. Now, furthermore, the degradation of these plastics, right now, it's kind of not balanced because we have holes and we have some electrons on the outside conduction band. So what happens is the O2 will react with these free electrons, and the H2O that's created will basically react with holes. And what happens is we create these radical ions, which are O2 minus and OH, which takes away the electron but also creates an H plus ion. And these radical ions, through a series of processes, along with the H2O and the light, will degrade polystyrene in this scenario, or other microplastic, down to a basic form, such as amethylstyrene. And although these will be in the solution, there are chemical reactions that cause methylstyrene to fully dissolve and create CO2 and water.
On to our independent variables. Just as Anisha was mentioning, our IVs are based on different semiconductors. ACL will be using bismuth oxide iodide as our first one. This is simply a comparison to the article Khairuddin et alia, which you'll hear me to refer to a lot. It is one of the foundational pieces for our procedure. So we want to test this semiconductor in order to just make sure that through our detailed procedure, everything checks out and the results are in accordance with what has already been published. Then, in addition to that, we are testing titanium silicon oxide as our second semiconductor, and this will be on a plastic of polystyrene, just like Khairuddin et alia. This is for our initial data collection. However, in the future, we will look at different plastics, likely polyethylene and PVC.
Okay, so for Huazhong's side, the semiconductor bases that we are testing on are bismuth vanadate and bismuth tungstate. And for plastic, in addition to the polystyrene that ACL is also testing on, we are adding polyvinyl chloride from the PVC tubes, as you can see there, and also polyethylene terephthalate from the PET plastic bottles. Yep.
On to research questions. At ACL, we are testing the microplastic degradation efficiencies of a composite of titanium, silicon oxide, and magnetite nanoparticles, along with bismuth oxide iodide and magnetite microsumers.
Yeah. And for Huazhong, we are basically doing the same as them. We are also investigating the microplastic degradation efficiencies of our two independent variables, which are the semiconductor bases. And also, since we are testing on a range of microplastics, we are also investigating how the efficiencies differ when the different microplastics are degraded.
Now for some justification on why we're using each of our semiconductors. VIOI, I've already mentioned this. This is just a control to refer as a reference to other material that's been published in this field. Then for TiSiO4, based on past papers that have been published in regards to biomedical microsumers, titanium has a low band gap and it has a very promising usage in the field of microsumers, but it is expensive. Now the problem with that is, of course, we want our technology to be spread, we want it to be used on a larger scale. So in order to combat that, we are creating a composite with silicon dioxide because it is a commonly found cost-effective material. And we have some past precedent for this being done. In biomed, we've seen Singh et alia in 2017 successfully synthesize a composite of SiO2 and TiO2 microsumers with good results.
We'll be using bismuth vanadate because it has already been done before. And the difference here is that we are going to try on different microplastics that have yet to be done. We do this so that we can test the relative performance of bismuth tungstate, which although it has never been used on microplastics, literature review has failed to show us any piece of literature that has shown its degradation on microplastics. It has shown excellent degradation of textile fibers. And because the electrophoresis movement and the band gap of bismuth tungstate is similar to that of bismuth vanadate, it means that we hypothesize that bismuth tungstate is going to perform similarly as well as bismuth vanadate. And so if we compare the two different microsimilars, we will be able to see the relative performance of each of the microsimilars and see how they can be used in a larger industrial context.
Starting off with our methodology, we first just purchased some microplastics. What we will be doing is purchasing a 1.1 micrometer solution of microplastics from Sigma Aldrich. This is something that we will all be doing because it provides a very easy comparison to Kyrudin et alia because that is the same exact one they used. Okay, yeah. Going on with the synthesis of the bismuth oxide iodide nanoparticles, first we begin with a potassium iodide solution and we pour some bismuth nitrate powder into that solution. Then we take that mixture and we put it into an ultrasonic bath. Essentially what that is just a tub of water that shakes a lot. So we put that in. After the color changes to brick red, the solution will be stirred for 5 hours at room temperature. Then it will be put into a centrifuge where the nanoparticles will be separated for later use. Now onto the synthesis of the TiSiO4 nanoparticles. We will take TiSiO4 powder, which will be purchased in that composite form, and mix it with water under magnetic agitation. That will be heated on a hot plate, and once that is thoroughly mixed, it will be sealed for later use.
On the Huajun side, we will dissolve equal number of moles of bismuth nitrate pentahydrate and EDTA. EDTA will act as a chelating agent. So what a chelating agent does is that it controls the speed of the reaction. This ensures that we can maintain nanoparticle sizes instead of it clumping together. And then after that, to a separate solution, we will prepare some potassium vanadate. Then we will place both solutions into an ultrasonic bath to disperse them. Then after that, we'll add the potassium vanadate solution dropwise into solution A, which is the bismuth nitrate solution. We'll autoclave it in order to increase the speed of each of the molecules, kinetic particle theory. And then after that, this encourages reaction happening between the bismuth ion and the vanadate ion. And then we'll cool it, collect it, and the green PPT that we'll wash will be the bismuth vanadate. For bismuth tungstate, it's quite a similar procedure. This is also a precipitation reaction. So similarly, we'll use bismuth nitrate pentahydrate and aqueous sodium tungstate under magnetic agitation. We'll then transfer the solution into an autoclave to encourage reaction again. We'll collect the residue, wash and dry overnight. After that, we'll calcine the residue. This means that the impurities in the compound will be removed through calcination, and it creates something called phase transformation, where we have a structure that is much more uniform.
Okay, so moving on to the synthesis of the magnetite, the nanoparticles that will be coating onto the microsimilars. We'll first dissolve the two hydrated salts containing the iron 2+ ion and the iron 3+ ions in deionized water. Then we'll stir it, and we'll also add the base, which is the aqueous ammonia, until it reaches 60 degrees Celsius. And we will then isolate the precipitate, which is now magnetic, via magnetic decantation using a magnet, and wash it with deionized water.
For the synthesis of the microsomers themselves, we start off with dispersing and stirring microsomer powder in deionized water, which we have created the microsomer powder in previous steps. Then we disperse the magnetite powder in deionized water as well in an ultrasonic bath. Then we take the magnetite and we inject it dropwise into the microsomer suspension until it reaches a 1:2 molar ratio, which we are basing off past precedent in our literature review. This suspension will be transferred into an autoclave to be heated. Then once all the excess liquid has been evaporated, this will be cooled until it's room temperature and put through a centrifuge. The pellets remaining will be rinsed with ethanol and deionized water until the pH reaches 6 and the microsomer pellets are dry.
Now on to characterization of microsomers, basically making sure that the microsomers have been formed correctly and are ready to test. First, we use the UV vis to to measure the absorbance spectrum of the microsomers, and we have to make sure that it absorbs all wavelengths of visible light. Next, we're going to perform FTIR measurements of microsomers, and this allows us to locate and to learn about the functional groups that make up the solution, and we can test those and compare those to what we predict are going to be the amounts of functional groups in the solution to determine whether we have made microsomers correctly. And finally, we're going to use the SEM, which is a microscope, and look at the structure of these microsomers and see whether they look like the images in Chirudin and CASTAR.
To control a photoreactor, we simply just build a box. And on that box, we cut out a hole on the top, and we just put a 50-watt LED white lamp into it. Then we'll just cover it up with aluminum sheets, then paint it black. And to do the microplastic removal efficiency test, we just need to prepare solutions of hydrogen peroxide. Then we'll just put a buffer solution, which is explained here, into the hydrogen peroxide solution. This ensures that pH stays at 7, and it does not affect any of the absorption or the degradation efficiencies of the microsomers. We'll then put the powdered microplastics into that solution, then put the microsomers inside the solution, put it inside the photoreactor, and irradiate for 120 hours. For each microsomer and each microplastic that we're doing, we will carry out the experiment 5 times.
Okay, so moving on to our data analysis. First of all, we are analyzing the movement of our microsomers in order to see if they have been formed correctly in order for them to move throughout the H2O field, and calculate the translational velocity, which I'll explain later. So first of all, on the cleaning slide of the microscope, we'll mix all of the necessary materials, including the microsomers of different semiconductor bases, and the microplastics, and also the field, H2O. And then we'll capture 10 seconds of movement of the microsomers using a camera that will be attached to the optical microscope. And then in which we will analyze the x and y coordinates of the microsomers at 0.1 seconds intervals and calculate the translational velocity of the microsomers using the ImageJ software.
So once the degradation of microplastics occurs within the solution, we know that H2O and CO2 will be produced. And the prediction is the CO2 will escape as a gas outside of the vials. So we're going to use a microscale to measure the masses of each of the vials to ensure that carbon dioxide has released, and we know that the amount of carbon dioxide produced is proportional to the amount of microplastic degraded, and that can tell us how much as a percentage of the microplastic has degraded. Next, we're going to use the UV-Vis again, but this time we're going to look at absorption spectra between two different semiconductor bases, and we assume that it's going to start off at the same wavelength. But after degradation has occurred, what happens is the absorbance will decrease because the amount of polystyrene or other plastic in the solution has decreased. So we're going to look at the peaks. There are going to be 2 peaks, and we're going to observe by how much it has changed. For example, if we have 2 solutions with these 2 different microsomer bases, we can see that this one probably degraded more microplastics because the peaks are farther apart, so it has degraded more rather than this one, which has degraded less. In addition, once again, we're going to perform FTIR measurements, but this time we're going to perform it on the solution, and what we're looking for in this case is the creation of organic groups, organic functional groups and compounds that are created when the polystyrene degrades.
Okay, so last but not least is our communication text. So first of all, we'll be using WhatsApp as our main platform of communication, be it text or sometimes talk. And also we'll be doing our bi-weekly check-in, this to ensure that everyone is doing their part and our progress will not be hindered. Yeah. So after the start of experimentation, the sharing of progress will be done through Zoom platform, as I think you'll I think it's the most accessible for all of us. And finally, we'll create a Google Drive folder to store all of our information of our data which we have collected from our experimentation, be it spreadsheets or Google Docs. Yeah. Here are our references. Thank you.
Oh, right. So this was not explained very clearly, but simply put, it's because visible light causes the microswimmers to move, and so we don't want it to move until the experiment starts. Which is why we have to put it in a closed box and turn on the light. It goes boom, and then yeah.
Also, we painted black because we don't want the light to escape. Right? We want it to be absorbed and we want it to be controlled.
We so basically measuring how much microplastic is degraded through the release, the change in mass through the release of CO2, right? If I'm understanding
Correct,
correctly.
that's all for
Would oxygen that's being produced in the reaction and then being released affect this mass as well?
Oh, the oxygen doesn't escape the solution because it's used in the mechanisms of microplastic movement. So it's used by the micro swimmer to move, and also it performs chemical reactions with the microplastics to degrade, so it doesn't get released as the